So, okay, I have seen many of you in the class. So, it's not yet 12 o'clock, right? Still, we have got a couple of seconds, I guess. Okay, fine. So, in yesterday's class, I was trying to tell you about choosing my subrectangle R prime to be consisting of all the points in R2 in such a way that x minus x naught is less than equal to 8 and y minus y naught is less than equal to mx. Okay, so over there I told you that in many cases what they do, they consider a rectangle minus into a cross minus b to b, okay, minus b to b, something like this, and then they decide on the extent of the x interval in the neighborhood of the point x naught. Okay, so I will come back to that. I will come back to choosing this x again. But let me tell you, let me get back to what I stopped yesterday. So I was talking to you about, say, suppose this is my rectangle R. Okay, this is my rectangle R, and I have a situation like this. This is x naught. So this point is going to be x naught minus a. This is your x naught plus a. Similarly, this is your y naught. Then y naught minus b. Y naught plus b. Okay, y naught plus b. And then I told you that in this subrectangle or in this rectangle R, I told you about the significance of the right hand side of this given equation. Okay, I told you that if, say, f of xy less than equal to m, then what happens? Like if you draw two lines, your y minus y naught equal to m, this, and y minus y naught equal to minus m, x minus x naught, passing through the point x naught y naught, then all your solution curve, whatever solution curves you are going to get through this passing through the point x naught y naught, they must lie in the shaded portion. I have already explained this to you. Okay, fine. So now let me come to another, related things with this rectangle. Okay, so these things, it has been, I think, in Codrington's book, in 1 or 2 pages they have described about it. Okay, and in many of the lectures, even if you follow the NPTEL lectures, you will see that they are drawing this kind of region throughout the illustration of the proof of the theorems. Okay, fine. So now, and let me tell you why. This shaded portion is very important. And of course, what is going to happen? Like that, we generate a sequence like y n equal to. Of course, these are sequence of functions, and then if we consider the graphs of all these functions, then they are going to lie in this shaded region. Okay, so now let me come to another point. Okay, fine. So yesterday, I told you that I'm going to emphasize on the corner. Okay, fine. Say for the time being, let us assume that. Like the slope of the curve, or slope of the solution curve, I mean it is positive, say. Okay, and suppose if I join this point x0, y0 to this corner, x0, y0 to this corner. So then, suppose this is something like this. So I should get something like this. Okay. So this is going to be my line y minus y0 equal to m into x minus x0. Is it okay? Suppose I am assuming that the slope of this line, it is say m1. Say. Okay. Then, so this line is nothing but y minus y not equal to this. Of course, I am assuming that your m1 is positive. Fine. Is it okay with everybody?
Yes, sir.
Fine? Yes. So now, what is going to happen? Like if your this is my bound for the function f of x comma y. So that is nothing but the bound of the slope of the solution. Is it okay? It is nothing but the bound of the slope of the solution. Because see, if you draw the solution curve, I mean, it's not necessary that at every point you are going to have the same slope, right? At different points you are going to have different slopes, right? So the slopes are bounded by that number n. Okay. So now what is going to happen? Say suppose this m is less than equal to m1. Okay. Then that is always guaranteeing me that all the solution curves, whatever solution curve I am going to get, it is always going to lie below this straight line, isn't it? Is it okay? Yesterday I had already explained this to you. All right. If you have any doubt, just let me know. Yesterday I had already explained, like, isn't it?
Yes, sir.
Yes. Okay. Now let us come to the condition. When your m is going to be greater than m1. When m is going to be greater than m1, then what is going to happen? I can get the solution curve in such a way that somewhere, I mean, the solution curve may be something like this, like say, my solution curve may be something like this. Okay, so that if I draw this slope, right, that slope can be greater than the slope of this line. Okay, fine. So again, I know that if my slope is capital M, if capital M is greater than M1, so obviously what is going to happen? I will have a situation like this. And what is going to happen? So this line is nothing but y minus y0 equal to m into x minus x. Okay, so that means there is a possibility that the solution curve is going to leave. The interval given by x minus x0 less than equal to x. Leave the interval, isn't it? Sorry, leave the rectangle R, for some value of x lying in this interval, as we did in the last part of the proof of the uniqueness and existence theorem. So I may have a point x1 where the solution curve is going to leave this rectangle R. Is it okay?
Yes, sir.
Yes, sir.
Fine. So that
Yes.
means if I consider my subrectangle, R also to be simply equal to R, so at all points in the subrectangle R prime, this condition is not going to be satisfied. Isn't it? Right? At least I have seen that x1 it is going to leave the curve. So somewhere in the interval, that particular condition is not going to be satisfied. Fine? Because we have already seen the evidence yesterday, isn't it? Are you getting my point or not?
Yes, sir. It is
Yes, sir.
here, slope of our solution curve is bounded by m, but it is not necessary that it should leave the rectangle.
It is not necessary that what?
The curve, our solution curve should leave the rectangle, but there is some chance.
Like see, I am saying that originally I was telling that if you join this point x0 y0 to this corner, you get a fixed straight line. You get a fixed straight line, and I am assuming that the slope of that straight line is m1. So now, okay, and the general case, let us assume that this is valid. Okay, let us assume that this is valid, and I am assuming that this m is strictly greater than m1, right? So then definitely I can have a situation like this. You agree or disagree?
Yes, sir.
Right? If I have a situation like this, so there is a possibility. Say, suppose I consider, although this interval looks bigger, you assume that this is a very small interval in the neighborhood of x0. So now, if at this point itself, this happens, then definitely here, somewhere in the neighborhood of here, the curve, suppose my curve was something like this, it is going to leave my region R. It is going to leave my region R. Isn't it?
Yes, sir.
Right? So that is why, in many books, they give certain limit for the rectangle R. Okay, I'll restate that. I'll restate uniqueness and existence theorem by redefining the subrectangle R prime. Okay, so earlier I had defined subrectangle R prime to be simply, the cross product of the intervals given by mod of x minus x0 less than equal to h and mod of y minus y0 less than equal to mh. Okay, so now let me tell you one thing. So here, suppose I am trying to find a subregion. In the given rectangle R in such a way that the solution curve does not leave R. Okay, so solution curve doesn't leave that subregion. Okay, and there is another restriction to me is that I have to keep the range of y fixed. So suppose I cannot violate these range. Okay, so the only way possible for me is to vary the range for x in such a way that the solution curve never leaves the subregion inside the region R. Fine. So suppose that is the case. So that is why now, if instead of this earlier case, if I take, say, I'm just telling you about possibility, but later on I'm going to give you some concrete things so that you are going to convince. So if I now take my subrectangle R prime to be minus B to, see, this is fixed. This is I cannot change. I have already told you. Okay. See, if I take this to be your, say, maybe if I take this to be your, just a minute. Should I? This was x naught. This is x1. This is x1. Say suppose this length is epsilon. This length is epsilon. Say suppose if I take it as x naught minus epsilon, x naught plus epsilon, right? Where x naught plus epsilon equal to x1. Say. Okay. So then obviously, if I take like something like this subrectangle now, in this subrectangle, my curve is never, solution curve is never going to leave this R prime. Is it okay? Fine?
Yes, sir.
Okay. So now you see how I can get that. Say suppose I know the value of m. Suppose I know the value of m. Okay. So now if you concentrate on this, then what is going to happen? You already know that. Let me just remove all this stuff. You already know that this length is b. Okay, fine. So then this length, what must be this length?
X1.
Okay, this length, okay, x1 in terms of b and m, if I want to write it.
That length is epsilon. Mod x.
Okay, see, okay, fine. So that means here,
B by
this is x1. Okay, so I know that b by x1 equal to m. Fine? Isn't it?
yes, sir.
Because it is nothing but the tan theta, the angle made by that line, right? It is the slope of the line. Okay, so that means your x1 equal to b by m, right? Fine. So that means suppose I have fixed b here. I cannot change the y bands. Suppose now I take your r prime to be your xy belonging to r in such a way that your just I am not even going to tell about y y bands. Where your this it's equal to minimum of a b by m. My job is done. Is it okay?
Sir, x1 notation is not clear to me.
Which is not clear?
Notation, you just draw a triangle and the below side you took it x1.
Okay, fine. See, this point is your x naught minor. Fine. Okay. In fact, let me not call this length as x1. No, this length is x1 minus x naught in fact. Okay.
Yes.
Fine. Okay. Let me call this length as x. Fine. Okay. So then let me simply change it to then my job is done. Fine. Now it is
Yes, sir.
now Yeah, thank you. I think you have, I mean, rightly pointed it out. Okay, now it is clear. Okay, fine. So,
Yes, sir.
whatever may be, say, suppose I have chosen an original rectangle where I am keeping the range of y fixed. Okay, of course, range of A is also fixed for the time being. But if I choose a neighborhood of the point x naught in such a way that x minus x naught less than equal to h, and h is the minimum of this, then by no means the solution curve is going to leave this subrectangle R prime. Is it okay now?
Yes, sir.
Yes. So that is why in all, not in all books, in some other books, particularly Codrington's book, he will write whatever, I mean, uniqueness and existence theorem he is going to write. I mean, in all of them, instead of the subrectangle, when I stated that Picard's uniqueness and existence theorem, there was, I mean, no mention. There was no mention of the subrectangle, I mean, explicitly. Isn't it? There was no mention of the subrectangle, I mean, explicitly. We assume that to be like that. Okay? We assumed it to be like that, and it worked. So now probably you have understood why the assumption, why the assumption worked. Now I think you know it. Is it okay? Fine?
Yes.
Fine. So
Sir.
here you can see that B is simply equal to MH. Isn't it? B is simply equal to MH. So that is why it worked. Now, I have seen, I mean, in no book they give the explanation, but I think this kind of curiosity you should have. You shouldn't, I mean, straightforwardly, I mean, accept. I mean, why this? You will see that everywhere they are going to write it as where H equal to minimum of A comma B by M. So this is the reason behind it. Is it fine? So similarly, you don't need to worry about it. Like say, because I mean, this is mod. This is mod. So then what we can do in this. So this is exactly once I have chosen this. Once I have chosen this. So then what is going to happen? What is going to happen? It is exactly. It is going to look like this. Exactly, it is going to look like this. Okay, fine. Exactly, it is going to look like this. And then what is going to happen? In this shaded portion, you should expect your solution curve. Okay, your solution curve. So it is going to be something like this. Okay, so in this case, I have taken. This is the case where H equal to your B by M. Fine? H equal to B by M in this case. Okay? So that is one explanation. So now what we are going to do, we are going to work out some example, and after that, I will come back to this theorem again. I am going to give a stronger statement, okay, but with some weaker condition, okay, and after that we'll proceed. Okay, fine. So let us do that. I will.
Sir,
Yeah.
sir, I have a question. Sir, here H by M is less than A. So in this picture, H equals to B by M is coming.
Yes.
So when B by M will be bigger than A, then
No, B by M cannot be bigger than A. No. Because B by M cannot be bigger than A. I have chosen it in that way only. Okay, because I have kept B fixed. Oh, I have kept
yes.
B fixed. It is never
Sir,
B.
we are comparing between A and B by M. So in this picture,
sorry. In that case, I am going to choose A. My job will be done.
yes, so I just want to know when my minimum will be A, then what will be the geometrical concept will happen, and what is the geometric concept of B by M in
Now,
this
I have
picture?
already told you. See, initially what I did, I joined this corner.
Yes.
Is it? I joined this corner.
Yes.
So in this particular case, whenever your that M is such that, whenever your M is such that, in that case, I mean, this situation is going to arise. This situation is going to arise. It is going to be something like that. You can try at home.
Okay, sir. Okay.
Okay. In that case, this is going to be the situation. You try it. It is always made before. Sorry. So maybe let me show you what I'm going to do next. Yeah. So you please have a look at the. You can see the slide, right?
Yes, sir.
Okay, just look at the first problem. And second and third problems, that will be nothing but a variant of the first problem. So please have a look at that. Do you have pen and paper? Have you already worked out the first problem? Okay. So you have been right? X, Y. Okay, this is, they haven't given you a fixed one. Okay, so the first question is, for what points x naught, y naught does, the theorem is nothing but uniqueness and existence theorem. Uniqueness and existence theorem imply that the given equation has a solution. So the first question is about existence of the solution, and the second question is about uniqueness of the solution. Can you tell me? Yeah. See, here no interval is given. Okay? Whenever no interval is given, you have to take the entire R2. Okay, as your rectangle R. And then you have to check. You have to then eventually shrink that rectangle to some subrectangular region so that you can find the solution. If you can find the solution, then whether you can get a unique solution or not, that possibility you should explore. Is it okay? So the very first thing is whether this equation possesses a solution or not. Okay, by uniqueness and existence, what is going to guarantee that? What is going to guarantee me the existence of the solution?
Continuity of
Derivatives are continuous.
Continuity of f. So here, what is f? F of xy. This is equal to simply 10 xy to the power 2 by 5. Right? Okay. So this f of xy, it is something like a polynomial, isn't it? Right? This function is always continuous in the whole domain.
yes.
R2. Right? So definitely, I know that this equation has a solution, right? For some x naught, y naught belonging to R2. Fine? Okay. Now let us see where we can find a unique solution. Okay, where we can find a unique solution. So for that, what we have to do? We have to compute this. So this is going to be, anyway, I mean 10 by 3 into 2 to the power 5 and xy minus 3 by 5, right? Okay, so maybe I can write it like this. 4, 5. Is it 4? 4. Let me write it like this. Okay. Fine. So what does the partial derivative of f tells you?
This will be y to the power 3 by 5.
Sir, y to the power 3 by 5.
Y to the power 3 by 5. So what does it tell you now?
Yes, sir.
Yeah, tell me. Where can you get?
So this is not continuous
Sir.
at any point whose second coordinate is 0. That is a 0 point. At that
so
point,
this
it is not continuous.
This is y equal to 0. Y equal to 0. This is not continuous. Isn't it? Isn't it? Right?
Yes, sir.
Okay. So if you exclude that y equal to 0 line, so that means if you exclude that y equal to 0 line, if you exclude this line, okay, so then you'll be able to find some domain in the remaining part where I'll be able to find a unique solution. Okay, so basically, if your y naught is not equal to 0, it will allow you to find a unique solution. That's it. Is it okay?
Yes,
Isn't
sir.
it? Because I want my solution curve to pass through the point x naught, y naught, isn't it? X naught, y naught. Is it okay? Fine? Okay. So now let me come to the second part of this question. Let me come to the second part of this question. Fine. So the only thing that has changed now, is your y0 equal to minus 1. Y0 equal to minus 1. Okay. See, we don't need to bother about the existence of a solution, right? We know that whatever may be the value of x naught, y naught, we know that it has a solution. Isn't it? Fine. So, firstly, let us try to find out the solution. Okay. So after that, what I'm going to do, I'm going to impose the initial condition and then see what are the possibilities here. Okay. Fine. So from here, I'm going to get let me rather move this here so that anyway, 3 x dx. Okay, fine. So this implies this plus 1 is 2 by 5. Okay, so I'm going to get 5 by 2 y to the power. I'm making a mistake. This is simply 5 by 3, fine, y to the power 3 by 5, so that is equal to 7 by 3 x squared by 2 plus c, fine. Yeah, okay. So eventually I'm going to get y equal to this is also 5 by 3. Fine. Okay. Isn't it?
Sir, so we are not able to see you.
Oh, okay. Oh, okay. Sorry. I should block it. Okay. So let me first see the problem. So the problem you already know, and you have to show that it has a unique solution on some open interval that contains x naught equal to 1. Okay. And then you have to find a solution and determine the largest open interval a comma b where it is unique. Fine. Sorry. So now yes. I say here I still haven't imposed the initial condition. Okay, fine. Okay. Yes, fine. So now let us not worry about this. Let us not worry about this one. Now let us see what can give me a unique solution. Okay, or let's say what possibilities that comes out of this. What possibilities that comes out of this? See, we have already seen that. If y not equal to 0, right, it eliminates the possibility of finding a unique solution. Is it okay? Right? Are you getting my point?
Yes, sir.
So now let me see when can y not be equal to 0. Fine. So basically, if I want to see when y is equal to 0, y is equal to 0 means your x squared plus c, this 5/3. Okay, or simply this happens, isn't it? Right. So now, if I want to find the corresponding x in the real line, so then your c must be less than equal to 0, isn't it?
Yes, sir.
Yes. Fine. So, and basically, what is going to happen? You are going to get from here. You are going to get your y at plus minus isn't it? Yes. Right.
Yes, sir.
So that means what we will do in order to exclude the possibility of not getting a unique solution, what we can do, we can eliminate this possibility, because if I eliminate this possibility, then your y at x not equal to 0, that is going to be excluded. Fine, I'll come back to this again. Don't worry about it. I have some purpose behind this, why I am doing this. Okay, obviously you know that I can make y equal to 0 by plugging in some values of x. That is good enough for me. Is it okay? Fine, isn't it? By plugging in some values of I can definitely get it. Don't worry about it. I'll come back to this again. There is a special purpose behind this. Okay. So now let me try to find out the solution of this differential equation under this prescribed condition. Okay. So if I want to find find that out, so then you will see that if y equal to -1 and x equal to 0, then your c is going to be equal to -1 only, because see, this is like odd powers. Is it okay?
Yes.
Fine. So maybe I will just erase this. Okay. So right. Using y0 equal to -1, we get -1 equal to x squared by c 5/3. So this implies c equal to -1. Okay, and from there I get y equal to your x squared minus 1, y equal to x squared minus 1 to the power y equal to x squared minus 1 to the power 5/3 as my solution. Okay, as my solution. Okay, fine. So just bear with me for some time. I'll just graph you that solution. Okay. So just now look at the Okay, so what I'm going to do, the solution was for x squared minus 1, fine, power your 5/3, right? Okay. So can you see the solution?
Yes, sir.
Yes.
Yes, sir.
Okay. So now let me make it more precise. Okay. Now let me try to reduce the expense so that it is more obvious to you. So what I'm going to do is say x range from say minus 2 to 2. Okay. And then what I'm going to do, along with this, let me plot this line 0 as well. Okay, fine. So this is my curve. This is my curve. Okay. Is it okay with everybody? Is it okay with everybody?
Yes, sir.
Yes. Now I think you can see me as well as the fine.
Yes, sir.
Okay. So now see there's a purpose behind why I am
Yes, sir.
okay, fine. So you know that if you look at the given equation, like hopefully you have already written it in your or maybe I can even adjust that also for you. Don't worry about it. Okay, fine. That will do absolutely fine. Okay, now you can see all three. The blackboard, the graph, as well as me. Okay, fine. So now if you look at the given equation, then forget about if you forget about the initial condition, so definitely what is going to happen? If you forget about the initial condition, then obviously y equal to 0 is also going to be a solution, right?
Yes, sir.
Yes.
Right?
Yes, sir.
Y equal to 0 will also be a solution if your Are we back now?
Yes, sir.
Yes? Okay. Okay. I don't know what happened. I mean, something happened and all of a sudden it was gone. Okay. Anyway. So now let me come back to the solution again. Okay. Say here the solution to this equation under this condition was this, right? X square minus 1 this. Okay. So if I want to find out the points of intersection of this solution curve and the line y equal to 0, definitely I'm going to get minus 1 and 1 as my points of intersection. Is it okay? Fine.
Yes, sir.
Yes. And you know that whenever y becomes 0, whenever the initial point y naught, it becomes 0, like you cannot get a unique solution, isn't it? So whatever interval of definition I am going to take for this initial value problem, it must include, it must exclude the point x equal to 1 and x equal to minus 1. Is it okay? Fine?
Yes, sir.
Isn't it? Otherwise, I am not going to get a unique solution. Is it okay with everybody? Now, is it clear what I am trying to get?
Yes, sir.
Yes? Okay. So now, so that means I can get for this particular initial value problem, I can get a unique solution in the intervals this, okay, this and this. Is it okay? They are the three possibilities.
Yes, yeah.
Fine. They are the three possibilities. Okay. Now, let me redefine the solution curve. Okay. Because earlier I told you about some piecewise continuous solution. If you recall my second or third class. Okay. So now I can also do something like this. I can also define my solution to be something like this. This is equal to your x square minus 1 5 by 3 if x is strictly less than 1 mod of x, and this is equal to 0. This. Okay. So then my solution card will look like this. Isn't it? It can still be a solution.
Sir, will it be differentiable at the point 1 and minus 1?
It can still be a solution. It can be a solution passing to that point. I'm just talking about only possibility of the existence of the solution. I here say, suppose the uniqueness is not coming. So this can be a solution to this given differential equation, right? Isn't it?
Yes, this can be, but we should have differentiability of solution curve also.
Yes.
Will it be differentiable if we define this function in this manner?
Yes, it should be.
Yeah,
it should
then okay.
It should be. Yes, it should be. Okay. See, what I'm trying to get is I'm trying to find out the largest interval on which this initial value problem has a unique solution. Can you give me the largest interval? I want to come to that. All these things I'm showing you because of that only. Largest interval.
Same minus.
the largest interval on which the solution we can have a unique solution. Basically, I am trying to ask you what is going to happen in this and this. Of course, in this and this, can I have two solutions?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
How? But I'm avoiding the point x equal to -1. So, yes. Why? Right? We can have two solutions like that. But yes, we can have solutions like that. So that means the solution is not going to be unique, isn't it?
Yes, sir.
Fine. The solution is not going to be unique, right?
So largest interval is -infinity to -1 or 1 to infinity.
Just a minute. Let me try to. Yes. Yeah. Fine. For the time being, let it be fine. But I still want you to slightly tilt. If I do it like this, what is going to happen? What is going to happen?
Sir, it is not the interval.
Which is not an interval.
Because mod x less than plus minus 1 are not there. So
Plus minus 1. But plus minus
So
1 is given.
open interval.
sir, if mod x less than 1 and mod x greater than 1, we choose that. Then the domain is only not the interval.
I'm not getting it. Your mod.
Sir, actually, you are excluding this 1 and -1 points from this domain.
Exactly. No.
So this you want to say.
Okay. Suppose I am including one here in this graph. So then what is going to happen? What is going to happen? Then what is going to happen?
Between
Is also a solution.
between minus.
Then what is going to happen? Then I can have like say in just a minute. This is no. I just want to. Okay, I have a graph passing through this point. No, I'm just trying to explore. Like I have a solution passing through this point. Okay, and yeah, because this is y equal to 0. This is y equal to 0. It is not passing through. It is not passing through this point. Okay, remember this is our initial condition. This is our initial condition. Okay, so anyway, like the largest interval is going to be either your see again you will say how can this be the largest interval? They must contain the point. I mean this, right? Isn't it?
Yes, sir.
Yes, sir.
Sir, actually, we have to think if we can.
So what is the
extend
largest interval?
the neighborhood of this initial point.
Yeah. So what is the largest interval then?
-1 to 1.
-1.
Exactly. -1 to 1. That's it. Is it fine now? I hope the confusion is going to make you understand the concept better. Don't jump into conclusion. Is it okay now? Huh?
Yes, sir.
Largest interval is yes, the open interval -1 to 1. Okay, fine. Now let me come to another one. Suppose this is so. What will happen then?
Sir, actually,
Yes.
sir, initial condition is y0 equals to 1 in the previous.
Yes.
But,
Now I have changed it. Yeah.
Okay. Now this is 1.
Now this is 1. So then what is going to happen? Then C is going to be equal to 1 only, right? If y0 equal to 1, y0 equal to 1, yeah, then C is equal to 1. Isn't it?
Yes, sir.
Okay, fine. So then, if C is equal to 1, my simply solution is going to be y equal to your x squared plus 1, 5 by 3. Okay, so then your solution curve is going to look something like this. And this is 1, this is 1, this is 0. Okay, this is y equal to x squared plus 1 to the power 5 by 3. Okay, so now what about uniqueness here? Yeah.
Now this curve does not cut x-axis, so here
Yes.
interval of definition is r.
You can never get an intersection of this curve with the line y equal to 0. Fine? Isn't it?
Yes, sir.
Right? So this curve is never going to encounter some point like this. Is it okay? Fine? Yes? I have
Yes,
already
sir.
fine. I have already found out that if your y0 is not equal to 0, you can always find a unique solution in that region. So here, what will be the largest interval?
Polar.
Minus
Yes,
infinity.
minus infinity. I hope it is clear now. Okay, if we are to find the largest interval, how to go about it? Okay, see, you should always seek the constant solutions also. Okay, fine. You simply plug in the right hand side, that is f of xy to be equal to 0, and from there you find out the value of y. Okay, and they are going to give you the constant lines and see what happens with the constant solutions. Okay, fine. So this is one thing, and then let me show you another. This thing we have already done. This was the next question. And now please read this carefully. Please read this carefully. This is very important. Okay, the remark. Please read this remark. Okay, so what it says that the existence theorem, the condition, like the continuity of the function f of xy and its first order partial derivative with respect to y, they are simply sufficient condition. Okay, if these two conditions are satisfied, definitely you are going to get a unique solution in that domain. Okay, but if they are not satisfied, that doesn't necessarily mean that it doesn't have a unique solution. It may have a solution, it may have infinite number of solutions, it may have more solutions also. Okay, so that is one thing. I will give you I'll give you examples of that. Okay, so now what about question number 2? Can you answer me? So the question is now we can get back to our blackboard. The question is that say suppose this has a one parameter family of solution, something like g of your xy c equal to 0. Okay, fine. And of course, I'm assuming that both f and your fy both are continuous. Both f and fy are continuous. Okay, and suppose by plugging in two different values of c, I am getting two curves. Say y equal to phi 1x and y equal to phi 2x as two particular solutions. Okay, so now the question being asked is why they cannot intersect, or why these two curves cannot be tangents at a particular point. Yeah, I think it is pretty straightforward. Can you tell me? Yes?
Sir, phi 1, phi 2 are the only solutions. Is there any condition?
No, they are saying that you cannot get two solutions given by this phi 1x and phi 2x in such a way that they are going to intersect at a point.
Sir, if they intersect,
Yes?
then at that point we can draw two tangent lines. But here dy by dx is equal to f of xy. So for a particular point, dy by dx is fixed.
How can that be? Why cannot I have a solution like this? This can be my phi 1x, this can be my phi 2x, right?
Sir, I think the definition of function is getting violated.
I think it will violate uniqueness, sir.
Exactly, that is what it is. Under the prescribed conditions, I cannot get this, right? See, when they are going to intersect like this, obviously that means I am having two curves passing through the same point. That cannot happen, right? And if they are tangent at a particular point, that also means that I am having two curves passing through the same point. Is it okay now?
Yes, sir.
Yes, that is right. So, and just a minute. I will give you. So, I will just tell you about this. I'll just tell you about this, and then I'll just do one exercise, and then the problem number 3 here at the bottom of the slide that you see, that I'm not going to walk out right now, but you simply see what is being given here. Okay, so you remember that expression 8. Hopefully you remember expression 8, right? During the proof, we got that. Or maybe I'm going to do this and then I'll come back to. Okay, fine. See, I mean during the course of this, what we did, we assumed that your del F del Y is continuous, both f and okay, we assume that this is continuous, and from here, what we did in the rectangular region R, I mean, I was taking 2 points, y1 and y2, for the same value of x, and from there I got your f of xy1 minus f of xy2, so this is del F del Y xy squared y1 minus y2 by being the root here, right? And from here, eventually we have found out that f of xy1 minus f of xy2, because from this continuity of this function in the bounded domain R, I can always get I mean whether y to be less than equal. I think we took it as k. We took it as k, right? So from here I can get, okay. See, I was able to prove that uniqueness and existence theorem with the help of this condition itself. Isn't it? Is it okay? Right?
Yes, sir.
Of course, this condition came from here. This condition came from here. The second condition. Okay, fine. But even suppose that I don't know anything about the continuity of the first order partial derivative with respect to y. But if I impose a condition that, okay, like the function, your f is such that I always have this expression bounded by some number k, then also I could have proved, isn't it? Right?
Yes,
Then
sir.
also I could have proved. Okay.
Yes,
Then
sir.
also then also I could have proved. So basically, you know what is this called? This condition is called
Lipschitz condition.
This condition is called Lipschitz condition. Okay, fine. And whenever a function f in some region R satisfies this condition, we say that this function f is Lipschitz in R. And in many books, they are going to write f is C-lip. So that means f is a continuous function and Lipschitz. Okay, in the domain R. Is it okay? Fine. So now you may be thinking, why this Lipschitz condition is so important? Okay. See, there are many functions. There are many functions for which the partial derivative may not be continuous, but still it may satisfy Lipschitz condition. Okay. So then what is going to happen? By simply making use of the fact that the function is Lipschitz, we will be able to find, we will be able to prove the uniqueness, and we will be able to find a unique solution. Is it okay? Fine. So that means earlier condition of fy being continuous, that was a very strong condition. Okay, fine. Now, even with a relatively weaker condition, we can still get unique solution. Is it okay? Fine. So that is why they tell you that in this way we arrive at a stronger form of the theorem. Now see, my theorem has become stronger. Why it is so? Can you tell me why the theorem has become stronger? Yes.
Because there are some functions which are Lipschitz but partial derivatives may not be continuous.
So that means earlier our choice of f was restricted. Now we can include more functions as f of xy. Isn't it? Earlier we only included functions f of xy such that its partial derivative exists. Now I will show you that you can even find some functions whose partial derivative doesn't exist, but still they are Lipschitz. So that means now I can include more functions, isn't it? So that means I am making my theorem stronger by making the condition weaker. Is it okay? I think they are also talking about making the condition weaker somewhere. Okay, fine. See, here is the nevertheless, somewhere they say about this week. Okay, anyway. So now I'm just I'll conclude today's class by just giving you an example. Just giving you that second example. Giving you the second example, what it is, f of xy. f of xy equal to x square mod y. Okay. Fine.
So we are not able to see.
No, yes. Don't worry. I'm here. Okay. Say what I'm doing. I'm taking this. I'm taking this function. Okay. So now. Now, is the partial derivative exist? Does the partial derivative exist? Del f del y?
No, at the point 0 does not exist.
Where?
The points where y components are 0, it does not
Okay,
exist.
it doesn't exist. Fine. Here, you already know how to go about it. Anyway, because mod y is not different.
Sir, except x equal to 0.
X equal to 0?
At 0, 0, it is partial derivatives are continuous.
0, 0 partial. Is it going to be continuous? I don't think it is. It is going to be
0 says at the origin it is differentiable, partially differentiable.
origin. It is going to be continuous.
Yes, at the
Origin. It is going to be continuous.
Yes, sir.
Yes, sir.
Doesn't exist. Okay, fine. Okay. Even I'm agreeing with you. Okay. Let me find. Okay, fine. So basically, you may be thinking why I mean, without like say arguing anything, I am concurring with you. Why I'm concurring with you? Basically, I want to tell you is that like say so at least I have some point. At least I have some point in the domain. I have some point in the domain, like okay, in this rectangle defined by mod x less than equal to 1 and mod y less than equal to 1. At least I have some points. Of course, I have infinite number of points where this is not continuous. Fine. Okay. So now, if I want to find out, say for 2 points, y1 and y2 for the same value of x. So then this is going to be giving me simply your mod of x squared, your am I fine? Am I okay?
Yes, sir.
Yes. Okay. So now, see your okay. Fine. So this is going to imply mod of y1 minus mod of y2. Fine. Okay. Yes.
Yes, sir.
So
Yes, sir.
from here I can write it simply mod of x squared, like say fine, and mod of x is less than equal to 1.
Less than or equal to 1.
Less than equal to 1. Fine. So I have found out that there is a constant 1 such that this happens for all your xy belonging to that square given by the R cell. Okay, fine. So despite f, the first order partial derivative of f with respect to y not being continuous at every point in the domain, right? It satisfies Lipschitz condition. That means even with Lipschitz condition, we can guarantee a unique solution. Is it okay? Right? So this is the reason behind, imposing Lipschitz condition instead of the stronger condition. Now it is clear?
Yes, sir.
Yes, sir.
Yes.
So I think I am going to stop here. So tomorrow I am going to talk to you about the syllabus of your exam and how I am going to conduct it. So please try to do all the assignments. Please try to do all the assignments and like say try to solve whatever problems there are in Simon's book. Okay, Simon's book or for that matter any source. Okay, I am not going to specifically tell which book to follow, which book not to follow. Even in Codrington also there are a lot of interesting examples. Okay, fine. So I'll meet you tomorrow then. Okay, bye.
Sir. Hello, sir.